So Ralph and I worked on this routing optimization project where we want to create a machine learning algorithm using classical and quantum approaches, where we've got an imaginary waste collection depot with almost 1,000 locations to service. Each location has between 2 and 6 tons of waste to pick up. You can have a maximum of 300 trucks, and each truck can carry 18 tons of waste. And each truck can only operate for a maximum of 6 hours and then return to the depot before it exceeds that threshold. And the data sets we have, also there's service windows where you can only visit the location between a certain number of hours. So we've got all these constraints, and figuring out this problem with one truck and which location to visit in which order in order to minimize the distance is complex enough. We're adding additional constraints here to make it more complicated. And this is a very real world use case. There's constraints that come up, and I'll hand it over to Ralph to talk about that. Ralph, you there?
He was popping in and out, so there might be
maybe yes, I'm here.
Oh, there we go.
Okay. So let me talk to you about the real life use cases. So as I mentioned here, the general version of the problem is known as the capacitated vehicle routing problem with time window. So it's a very well-known problem and very studied because it's widely used in many areas. One of them is e-commerce and delivery. I guess that would be obvious due to the nature of the problem. Like you would have a company that has to deliver a lot of things to many houses, and they have to optimize their way to economize time and also like tariffs, because it costs a lot to like the cars and everything. Anyway, you also have food delivery, where it's very challenging to respect the time because the food might perish during its way. You also have waste management and collection, ATM replenishment and cash in transit. Like, that there are human beings filling the ATMs. It's not that magic trick that fills them. So it also uses the optimizers for this problem. And you also have repair services and field technicians. So I will let Kai continue with the next part.
Thanks. So we're going to minimize the distance traveled. So we save fuel and wear and tear on the trucks. We're going to service all locations within the service window. We can compare the results from classical and quantum approaches. The approaches we took are k-means and db-scan clustering, reinforcement learning, graph neural networks, taboo sampler, and simulated annealing, much like Sandra had done. We were going to use the D-Wave solver, but as I said, we don't have the token yet, so that will have to wait on. We have the algorithm ready, just need to be able to run it, so we don't have those results, unfortunately. I'll just give you a quick overview of the data set that we have. So this is, and we targeted 999 locations. We did scale up to that, but we started with 26 just to get things going. And so we have results for both. So we have 26 locations here. The demand tells you how many tons to pick up. That's the load at each location that has to be picked up. 0 is the depot. So the trucks leave the depot at location 0. They visit however many locations they can. Within the 6 hours, they're allowed to run, and then they return. And a truck only goes out on one route, only visits one location once. It does it within the... the service time tells you how long it takes to service that location, and the arrival start and duration is the time window. So for location 1, for example, it opens 300 minutes after the depot opens. So I can only go there 300 minutes after, and it's only open for 60 minutes. All right, so that's the time window. And by the way, this data I got from D-Wave it was actually part of an interview assignment. So I based it off of that. And then when we went up to 999 locations, we just scaled it up synthetically using AI. And we have a distant matrix for each of the 26 locations. You can see the diagonal of zeros. This tells you the distance between each location. And it's a little off. For example, the distance from the depot to location 1 is 16 kilometers. If you look on the other side of the matrix, it's 15 kilometers back. The next one is 14 kilometers there, 7 kilometers back. So I brought this up to D-Wave. They didn't seem to care, but I did notice it was not really great data. And then this is the travel time. So it takes, same thing, but instead of just the distance, it's the travel time to get there. So this all figures into the algorithm when you're calculating, all right, how long did it take to get there? I service it. Did I get there within the time window? So the routing has to fulfill all those constraints. I'm going to hand this back to Ralph to just talk about his approaches quickly about with the different classical examples.
So basically, in the state-of-the-art approaches, we have 2 phases to solve the problem. The first one is to cluster the routes, and then solve the problem individually on each cluster. So that the optimization problem in the second part is computationally easier to solve. So here in these 2 approaches, we use the k-means and the dbScan solvers, which are 2 algorithms that are often used in research papers for this problem. And here I implemented a reinforcement learning graph neural network approach, which uses like a neural network to assign groups to the nodes. Again, it's about clustering, but using a neural network. And then the second part is also like for the routing, we use a classical solution.
Yep. So I used a binary quadratic model, which then fed into the simulated annealing and taboo methods. So I used the same BQM for each. And then the D-Wave example we're going to run, they already have a capacitated vehicle routing with time windows model, which is very handy. So we'll just feed that in. The algorithm's ready once we get the token. So the results were really interesting. I'm interested to see what the hybrid nonlinear solver comes up with. But on the 26 locations, the best result came from the Tableau sampler. And it did 343 kilometers in 7 routes. The processing time was quite high comparatively, but below is just an example of the route it came up with. So it had 7 trucks. These are the locations to visit in each order. You can see they start at 0, end at 0. That's leaving and going back to the depot. And so, based on those matrices, this was the best route, giving the lowest distance traveled. When we scaled it up to 999 locations, Ralph's k-means classical algorithm prevailed with the lowest distance traveled. He got it under 12,000, great processing time. And it was done using 235 routes, which I had a completely separate k-means attempt. We got the same amount of routes. I came in just a little higher on the distance. But yeah, very close. The simulated annealing didn't do quite as well. You can see that second column to the right. That went for 9 routes, slightly higher distance. So yeah, I think, if we can solve these, if we can shave miles off these transportation routes, we save energy, we save wear and tear, people get their products faster. I think this is a huge opportunity for quantum to really help us out, figure out these routing problems. As Ralph said, it's used all over the place. I think that's it. I think we're just under time.